Today I'm going to be talking about how to measure the quality of a deep neural network. So let's say you've built your network. How do you know it's good? Well, this all starts by structuring your data the right way. In our class, we're going to be using holdout validation. You've probably seen this before. What you're going to do is you're going to divide your data set into three parts: a training data set, a validation data set, and a test data set. The training data set is going to be used to train your model, unsurprisingly. The validation data set then is going to be used to validate that model. So you're going to use this data set to tune your hyperparameters and get the model tuned and get it as good as possible. Then and only then will you use your test data set, which is going to be held away to just give you a unbiased score of how good the model did. Now, in sort of like old school machine learning, you're probably used to like some split percentages here where you would use like, I don't know, let's say that you used 60% of your data for training and 20% for validation and 20% for test. Or maybe you used 80% for training and 10% for validation and 10% for test if you're feeling really adventurous. That like percentage split doesn't necessarily hold true in deep learning, or it's not necessary to take 40% or 20% of your training data and hold it out, because when we use these deep models, typically our data sets are really big. We have lots and lots of observations. So maybe we only had 10,000 observations in a traditional machine learning model data set, but now we're probably talking more like 10 million observations. In that kind of situation, it doesn't make sense to reserve 10% or 20% for a validation and test set. You might be able to get away with 1% instead of 10%. So that's a rule that we can break in this sort of deep learning world. Now, we should talk just a little bit about cost functions. Cost functions are something I'm sure you've seen before. If you want to think about a neural network as sort of a black box, how we will get a prediction is we will take our training data, our test data, or our validation data. In this case, I'm using test. We're going to show it to the network, and what we'll get is a prediction, which we'll call y hat. At the same time, we have the ground truth from our test set that we'll call y. We can use the cost function to measure the difference between y and y hat, and then we'll know how close we are. Now you can see from this slide, I'm suggesting that this would be like a regression problem and that we're using root mean squared error. Of course, there are lots of different cost functions. It very much depends on the problem that you're trying to solve. All right, now before we finish up, let's talk just a little bit about bias and variance. Bias, or is also called underfitting. So a model has high bias. It's underfitting when it's not complex enough to fit the training data. Variance is sort of the opposite. A model has high variance error, or it's overfitting, when it fits the data so well that it fits the noise in the training set as well, and so it no longer generalizes. And so what will happen then is the network will perform worse on the validation set or the test set than it will on the training set. Here's two common scenarios that I thought we might want to look at. In the first scenario, I'm talking about Bayes error. What's Bayes error? That might not be something you've heard of. Bayes error is our prior assumption about the best error that we could hope to achieve in the model. So what's the best we could possibly hope for in the model? Well, maybe it's perfect. Maybe it's not. Maybe you'd say that there's random chance in there and it couldn't possibly be perfect. So it's sort of our prior on our assumption about what the error is. If you're not sure what that should be, probably a really good place to start would be to assume human error. So the human error maybe for this problem would be 2%. Let's say that. So in the first scenario, we had 2% Bayes error, but our training error and our testing and validation error were both 20%. So in that case, this is a high bias model. The model is not fitting the data nearly as well as we'd like. So how do we fit the data better? Well, we can add model complexity. We can add neurons, we can add layers, we can change the architecture. Maybe an LSTM or an RNN are better architectures, and if you haven't heard of either of those, that's okay, we'll get to that later. Probably won't. What won't help in this scenario is more data. If you can't fit the data you have, you probably won't suddenly start to fit new additional data. The second scenario that's probably more common still is an overfitting or high variance model. In this case, you have some Bayes error that's 2%, and maybe your training error is 3%. So it's pretty close to what we would hope for our prior best case. The problem though is that when we go into our validation set, we find that the error is 30%. This means that we're overfitting to the training set, and we're not able to generalize well to data that the model hasn't seen. What do we do when this happens? Well, we have a couple of options. The first one is we can add more data. That's not always super easy. You can't always magic up data. And if that's the case, you can use data augmentation, which is something we'll talk about in just a few chapters. And as you can imagine, data augmentation is a way you can augment your data to make it seem like you have more than you do. Then lastly, you can use regularization to penalize the parameters that get too rambunctious and try to pull them back down so you're not overfitting as much. And you can use dropout, which is a neural network specific way to do regularization. We'll talk about both of those later. Probably what won't help is to add more complexity because your network's already too complex. So if you've done a lot of machine learning before, one of the things you might be asking is, what about k-fold cross-validation? It's better, right? It's what the guys on Kaggle use. That's right, it is better. K-fold cross-validation is definitely a better strategy. If you're not familiar with it, here's how it works. What you do is you take your data and you divide it into k-folds. Let's say in this example, in the diagram, I'm using three-fold cross-validation. So I take all of my data and I split it up into three folds. And then what I would do is I would train my model on fold 1 and 2, and I would use 3 to test. And then I would train it on 1 and 3, and I would use 2 to test. And then I would train it on 2 and 3 and use 1 to test. And so I would train my model 3 different times, holding it one fold out each time to do validation. This is a much better way to understand the error because you'll understand the error across the entire data set. Unfortunately, neural networks can take a really long time to train. Unlike a traditional model that maybe takes minutes or worst case hours, sometimes deep neural networks can take hours, days, or even months. And if that's the case, this kind of strategy just probably isn't going to work for you just because of the computational complexity and the time that you would have to give up in training. So that's a little bit about validation. I hope that sets the stage for the rest of the class and answers some of the questions you might have about how we'll validate our deep neural networks.